Okay, I think we're going to get started now. Thank you for everyone for coming today. This is Professor Kamath. He has very kindly accepted to be here with us today to give a talk on his research in differential privacy. We're going to start the first 30 to 45 minutes off with this talk, and then we'll leave the rest of the time for live questions. You guys probably also know the sign-up form since hopefully you guys filled it out. There are questions in there, but we'll focus on the live questions we have today. So if we could please give it up for Professor Kamath.
Cool. Yeah, thanks a lot for having me here. It's really good to, I really like engaging with the undergrads, but there's not really that much of an opportunity outside of class, so I appreciate the invitation and the chance to chat with some of you today. Yeah, my research, I'll say a bit more. I focus a lot on differential privacy in the context of machine learning and statistics, but I just want to get a feel for, this has been an interesting month even for machine learning, so I just want to get a feel for how much people have seen, and I kind of live in a bit of a bubble, so I'm just wondering if you're in the bubble or not in some sense. How many people here have heard of machine learning? Show of hands. All right, effectively everyone. How many people have played with ChatGPT? Okay, almost everyone, I think maybe everyone. How many people have heard of GPT-4? Okay, so still everyone. This came out only 10 days ago, this announcement, so it seems like people are pretty in the loop. Let me ask one question. How many people are afraid of AI and machine learning? I'll raise my hand. It's an interesting time, especially, like I said, the last even month has been a lot of very interesting, exciting things. And yeah, so I'm happy to take today as casually as people want. If people want to talk about differential privacy, that's cool. If people want to talk more broadly about machine learning, that's cool. I'm really happy to chat about whatever people think is most interesting at the time. So let me just, in case you've missed some of the examples, this is there's a paper by Sadbubeck et al., which came online, I think maybe literally 2 days ago. Just showcasing some of the power and capabilities of GPT-4. They titled the paper something like "Sparks of Artificial General Intelligence," which I hate because I think that title is filled with a lot of hype. But undeniably, GPT-4 and some of these machine learning models can do some incredibly powerful things. Like, you can ask it, can you give me a proof that there's infinitely many primes with every line that rhymes? And I'm not going to read it out for you, but effectively this is simultaneously it rhymes well, and also it's effectively it's a real proof of the fact that there are infinitely many primes with the letter S at the end. I'm not sure why, but besides that, it seemed pretty good to me. Other examples that are interesting. This is another prompt, which is literally some leak code problem. You're given a zero-index integer matrix and it has some examples. It makes some references even to the path highlighted in red, but it's just this text here. And so some constraints and hints. And in fact, this is what it outputs. It literally outputs working code, well commented and everything. So yeah, this is honestly, 2 or 3 years ago, totally unthinkable, unimaginable. I wouldn't have thought something like this would be so doable. So I think it's a little bit magic. But I think the problem that I want to highlight here is the fact that I think, we're building this boat of machine learning, a very amazing ship, but I see my role in it trying to, patch it up, take care of some of these concerns, which are maybe not quite as flashy as some of the amazing achievements that machine learning can do, and take care of some of these very sort of embarrassing failures of machine learning models to do even some of the most basic things that we should think that they should do. In particular, today I'm going to be focusing on privacy and how these machine learning models, when you train them without special care, they can just fail catastrophically in terms of privacy concerns. I've also done stuff in robustness, which I'll not talk about today, but I'm happy to talk about if people have questions. As you might have guessed, this is actually a machine learning generated image by Bing Image Creator. So yeah, let me tell you a little bit about privacy. So nowadays, all of these machine learning models that you see nowadays are really powered by massive amounts of data and frequently sensitive. For example, companies like Google, Apple, the US Census Bureau, these all use large amounts of data, which is very personal and sensitive in nature. And I want to show you that, in fact, it's very easy to violate individuals' privacy when you do machine learning on their data. So here's an XKCD comic, which you can see here the individual is at their computer, maybe on their email, typing in "Long live the revolution," our next meeting will be at, and they ask their email client to complete it, and it says suggests the docs at midnight on June 28th, suggesting that something illicit is happening on the docs at midnight on June 28th, which is someone else's secret. And so the caption says, when you train models on other people's on input from your users, it can leak information in unexpected ways. Now, this is of course just an XKCD comic, and it's just supposed to be a joke, but actually this is not so far from reality. Here's some very nice work by Carlini et al., which shows that ML models can leak lots of information about their training data. Here's a quote from the blog post on this paper, and they looked at GPT-2, a previous version, and they found that at least 0.1% of the generations, which is a conservative estimate, were copy-pasted from the training set. So this training data can be very sensitive in a number of different ways. For example, it can contain personal information. So if you prompt GPT-2 in the right way, it'll tell you some Peter W.'s personal information, mailing address, phone number, email, fax, which is maybe something that you wouldn't want to be spreading all over the internet. It can also contain, say, copyrighted content. If you prompt GPT-3 the right way, with say the first sentence of Harry Potter and the Philosopher's Stone chapter 3, it'll give you an entire page, which is clearly some sort of questionable copyright violation. So this is probably one of the more glamorous or like obvious things which a machine learning model probably shouldn't do if we want to pretend at least we care about privacy. And it's not just there. You might be thinking, okay, these huge machine learning models, they have unbelievable power. They can do all sorts of crazy things. Not so surprising. But even simpler cases, like very basic statistics, there's certain things that people care about in genomics and genetics called genome-wide association studies, or GWASs. This is what a lot of biologists do to try to find correlations between genetics and various diseases. And they don't use any super fancy machine learning model. They usually use things like chi-squared statistics, very basic statistical tests. And here is, I don't know, I'm not a biologist, but there's like some sort of illustration of what a GWAS study could look like, where you find correlations between different chromosomes and various diseases of different sorts. And so things which are higher up, that indicates more correlation between these. So these are, of course, crucially important to the scientific method and to discovering, genetics and connections with diseases. But there was a very interesting, of course, this operates on very highly sensitive medical data. When you're participating in such a trial, you really give up your genetic information, and that's not something you want to be leaked. For example, if you're participating in a trial which is looking at people who have some socially stigmatic disease like HIV/AIDS, then if your participation in such a trial were leaked, then this is a privacy violation. So ideally, you'd like to preserve the privacy of people who participate in such a study. Now, unfortunately, there was a very influential result by Homer et al., which actually showed it is possible to re-identify people who participated in such a study. And this set off all the alarm bells in the sense the National Institutes of Health, which essentially run a lot of these things and statistics releases in the US, they said no more, we're not going to put out this data publicly. Now you have to go through some vetting process, and they took this very seriously. So it seems like if you want to do this sort of analysis, you have to take into account privacy, or else you're in big trouble. And there's many more cases. These are just two examples. There's the Netflix prize. They gave away $1 million for a recommendation engine, but they were also sued because they essentially inadvertently leaked people's watch history. I think there's a anonymization bug bounty round 2. You can imagine what happened in round 1 and very quickly happened in round 2. Anonymization is a very poor way of protecting privacy. And then there's many more examples that go on and on. But the recurring theme, the bottom line, is that when you do large-scale machine learning and statistics on sensitive data, these inevitably violate individual privacy. And it seems out to be the case frequently that best effort or heuristic privacy measures don't work. Things like removing people's names, that's not good enough. There's so many other ways to identify for savvy privacy researchers or attackers. And it seems like the only thing that we can really do is go for a rigorous privacy guarantee to preserve user trust. By a rigorous privacy guarantee, I mean something where we can formally or rigorously prove that in fact, whatever we put out into the world, it will preserve users' privacy in this sort of theoretically principled way. It's not just trying for the best or doing something that seems good. This is something you can actually prove privacy is preserved. And that leads us to differential privacy, which is indeed a rigorous privacy definition introduced by Dwork, McSherry, Nassim, and Smith in 2006. So, 15, 16, 17 years old now. It's not, that's relatively young in terms of the grand scheme of things, especially for things which are, deployed at the level which they are. And I'm not going to formally define it for you. I'll maybe flash it in a few slides, but I just want to give you the feel for what sort of things that differential privacy is supposed to protect. So we imagine the following type of experiment, that there exists some data set which includes some sensitive data. It is fed into an algorithm, and that algorithm produces some sort of output. Now, we can imagine instead of that, we can imagine that there's another data set which were fed into the algorithm which produced an output. And you notice that these two data sets that we're considering are the same, except for the addition of one extra data point. So they're what we call neighboring data sets because they only differ in one entry. And the idea is an adversary will be looking at the output of this algorithm, and what the adversary is trying to do is really figure out which is the real data set. Is it actually X or X prime? Does it have this user's data in it, or does it not have this user's data on it? And if your adversary is unable to figure out which one it is better than, say, randomly guessing, then we say the algorithm is differentially private. So, this is an informal definition. I'm not really going to focus too much on the technical definition, but we say an algorithm is differentially private if its distribution over outputs doesn't change much after adding or removing one point. I'll discuss this a little bit more in the next few slides, but I'll pause here just because I've told you a lot and happy to take any questions if something's unclear so far. Yeah, back.
How does the adversary know which data sets could be possible?
Good, yeah. You're kind of asking the question as to why do they know it's either X or X prime? The idea is it is indeed a very strong assumption, but we're saying even if they had so much information, they've narrowed it down to either this data set or this data set, which is unrealistic in the real world, but even if they had done that, then they still can't tell which one it is. So that's such a strong guarantee that even if they had less information, they wouldn't be able to figure it out. Yes?
Yes, like a couple questions. So can the adversary choose the two data sets? Or is this the good guy who chooses the data sets?
Good question. The guarantee that the rigorous the rigorous definition essentially for any two data sets which have that property and differing on only one entry. You had something else?
Yeah, so this is a really strong definition. I'm guessing in real life, you guys use a weaker definition? Or do you guys actually manage to get this definition to work in real life?
Yeah, it turns out that in order to satisfy this definition, the nice thing is that there's some very well developed, a toolkit basically, it's not clear how to satisfy this, but the idea is that we have some basic building blocks, and putting them together in the right ways lets us build quite complex systems which satisfy this type of privacy guarantee. Cool. Yep, back there.
Can you say that the privacy issue comes because models memorizing rather than generalizing, or can you still have privacy problems in a model that generalizes?
Great question. Yeah, is this just a problem because memorizing instead of generalizing? It's more than that, because yes, memorization, there's something to that, but in fact, it's a privacy issue even if it mostly generalizes, but even 1 in 1,000 or 1 in 1,000,000 data points is memorized. So it's more to it than just that. Cool. Any other thoughts here? Yeah.
So are these algorithms deterministic or are they random?
they have to be randomized, and that's something in the definition, which I'll flash but not discuss too much, and I'm happy to talk about that more offline. Cool. Any other thoughts about the setup? Cool. Here is the formal definition, which is a little bit, it's weird the first 6 times you see it. 7th time it makes a bit more sense. But yeah, I'll read it out to you, but I won't dwell on it too much. Past this slide, we won't even need to worry about it at all. We say an algorithm is differentially private if for all data sets, like I said, any 2 data sets, x and x prime, which are neighboring. And for all kind of events, we have this, you can mostly ignore this delta, just pretend it's not there. But it's basically saying, changing one data point, that doesn't increase the probability of any event too much. So it's a quantitative definition, meaning like you can raise or lower epsilon and delta, and it becomes more or less private. Those are some typical parameters. But really, it just bounds the multiplicative increase in the probability of any event. So, if there's some bad event, then it won't become that much more likely by adding or removing one data point. Delta is like some chance of catastrophic failure, but that's not too important. So this is the definition. I feel like I'd be doing a disservice if I didn't show it to you at least, but don't sweat it too much. It's not super important for the rest of our discussion today. Maybe the only thing I will emphasize is the fact that, just remember that it's a quantitative notion of privacy where, like, if you have, I'll just claim it without discussing too much, but the smaller these numbers are, the more private it is, whereas the larger these numbers are, the less private it is. So think of 1, 0 as a pretty good privacy definition. But yeah, the question is, okay, so we've got this definition, and it's actually a pretty powerful notion of privacy in the sense that it can protect against pretty much any privacy attack that depends on individuals' data. Like, let me put it this way. My claim is that, just flipping back to this definition here. The claim is that the output of the algorithm is roughly the same if you add or remove one person's data. So therefore, anyone looking at the output shouldn't be able to figure out too much about that person's data because it's pretty much the same as if they weren't in the data set in the first place. So it kind of protects against all of these things that I've shown you, which are very individual dependent and leaking individual data. So that includes things like database reconstruction, which finds and uses private data, membership inference, which is figuring out whether someone participated in a medical trial or not. And at a broad level, it's like learning anything about a user that couldn't be inferred without them. Any sort of individual privacy attacks. Cool. So this is a very popular notion of privacy in the sense that it's accepted in theory. This is Kurt Gödel. The Dwork et al., they won the Gödel Prize for this, which is like the top theory prize in theoretical computer science, but also it's been deployed in practice at Google, Apple, and the Census Bureau. I'll focus a little bit more on this last one. So the United States has a decennial census. Every 10 years, they essentially try to count how many people are in the United States and various demographic information about them. For example, what race is, what income level, stuff like this. And this sort of stuff is very sensitive data in the sense that people's race and characteristics like that are often considered sensitive. So in the 2020 version of the census, they actually use differential privacy to protect these counts because they're required by law to preserve privacy of the people who give their data. And this was a very bold move. It's can you imagine? It's kind of surprising to me that from being introduced in 2006 to being used on 300 million American sensitive data, it only took like 14 years, which I think is a very short road for something of that importance and magnitude. In particular, there's actually literally been lawsuits over the use of differential privacy in the US Census. The state of Alabama sued the Census Bureau for their use because these are very high stakes decisions that are made based on census data, like districting, choosing, how many districts there will be in a state, and these affect people's real lives. So it's very high profile in terms of some of the deployments. Another example, which is a little bit more, less high stakes, is Google after COVID-19 started. they were doing some community mobility reports to understand where people were going after COVID that differed from before. And so, this phone knows exactly where I am, for the last roughly 11 years since I've had, smartphones, which is a bit creepy. You can turn it off, but I find it actually kind of useful sometimes. So the truth is probably many of your phones are tracking you as well, and Google has all this data. So what they could do is they could just publish where everyone is, and they'll probably get sued into oblivion. But instead what they did was they released some information about where people go before and after COVID with this data aggregated and protected using differential privacy. So for example, you can see that these are right after COVID started in 2020, and you can see that parks and workplaces and transit stations were significantly less occupied than they were before, whereas residential is somewhat higher, which matches maybe what you think. Cool. So I've told you a bit about what differential privacy is, where it has been used in practice in a few places. I feel like I'd be doing a disservice if I didn't show you at least one private algorithm, just so you know how do you actually make sure something is private. And I'll show you the most basic, simple type of way of privatizing something. It's literally going to be the most baby question you can ever imagine, which is adding up a bunch of zeros and ones. So let's suppose we want to privately compute a sum. So everyone has a 0 or a 1, which could be maybe some sort of sensitive information. For example, do you smoke or not? Maybe you don't want to tell everyone this because, for example, if your insurance company found out that you smoked, then they'd raise your premiums. So this is sensitive data. So the naive way to do this is just compute the sum of how many people have smoked or not, but that, for reasons I kind of alluded to but didn't really say rigorously, could violate privacy. So instead, what we'd like to do is we'd like to release this sum subject to this notion of differential privacy. And it turns out that a natural quantity to look at here is understanding how much this sum can change if you add or remove a single data point. That seems hopefully natural because we're looking at, adding or removing one point. It's very natural to understand how much could that change the thing we're looking at. So that's known as the sensitivity. In this case, if you're adding together a bunch of 0 1s, clearly the sensitivity is relatively low. And so the claim is, if you add up these bits, but then add some Laplace noise, where Laplace is a distribution that looks like this, that is going to be a differentially private estimate of the true number of people who smoke, or the true number of ones. So it's like a Laplace distribution, but a Laplace distribution basically exponential, but two-sided. So it's a little bit abstract, but let me give you something a little bit more concrete. So using this exact same example I said, how many people smoke, say 20 people is the true answer. Then what we could do is we could guarantee 1, 0 differential privacy by adding noise to each thing. And so if you do it a few times, maybe you run it once and it gives you something that looks like this, 20.68. You run it again, it gives you 19.24, and so on, so on. If you want to guarantee even more privacy, then you have to add more noise. Seems pretty natural. So for example, if I wanted to guarantee 0.1 differential privacy, remember that the smaller this number is, the more private it is, then you get more variance in the numbers, 22.45, 11.45, stuff like that. So that's the most simple private algorithm. Add noise, which is bigger or smaller depending on how sensitive the function is and how private you want it to be. And that's like a general recipe. You can always just choose whatever function you want to privatize, compute how sensitive it is, and then add noise to it where the size of the noise is dependent on how sensitive it is. So it's a little bit reductive, but if there's one thing you can take away, one way, a common way to privatize statistics is to add noise to the outputs, and that'll make it private in some very rigorous sense. Now, this is about adding together zeros and ones, which is ridiculous, right? I started this with talking about machine learning models. This seems like a far cry from something like that. But it turns out, I don't have time today to get into all the details, but it's actually possible to use ideas built on this to train a machine learning model in an almost drop-in replacement sense. What do I mean by that? The way every machine learning model is trained today effectively is a method known as stochastic gradient descent, which I won't get into this too much, but essentially it follows the negative gradient of the loss function. If you know what that means, great. If you don't know about what that means, don't worry. But essentially, the way this works is it takes some quantity from each of the points in your data set and averages them. So that seems very close to what we were doing just now, right? Before we were adding together zeros and ones. What all stochastic gradient descent does is takes your data, does some transformation to it, and averages it. It's almost the exact same thing. So that's exactly the same intuition that we're going to use in the sense that there's a version of SGD, stochastic gradient descent, which is called DPSGD, differentially private stochastic gradient descent. And I hid a million and one details, but it's essentially the same thing. You just clip your gradients so they're not too large and add noise in a manner similar to what I showed you in the last slide. And if you do that, then pretty much any machine learning model you use DPSGD instead of SGD will satisfy some sort of rigorous privacy guarantees. And yeah, it's actually surprisingly useful in various settings. Like this in particular, okay, they use a slightly different algorithm, but it is actually used in practice. For example, if you've ever used the Spanish language Google keyboard on your phone, the Gboard, this gets information from users. So if you type in a word on your phone in Spanish, then it'll send it back to the mothership, except it'll do it using an appropriate form of differential privacy so that it's not leaked, what sort of messages you're sending your friends. So I think that's pretty cool. That's possible to actually generate useful predictions while simultaneously guaranteeing individual user privacy. Cool. So I'll just give you one slide about the type of question that I've been most interested recently in my research on, trying to understand how to use privacy in machine learning models. The big thing that all of these machine learning models nowadays are trained on public data, things which you just download from the internet. For example, GPT-4, the most latest one, they haven't stated exactly where the data comes from. They've actually been a little bit coy about where it comes from, like specifically saying we are not going to tell you where the data comes from, which I think is a little bit, I don't agree with that practice, but a lot of it is just downloading stuff from the internet. For example, a common source is, say, Wikipedia, which has a lot of high quality English language text. Project Gutenberg, which is out of which is books that have entered the public domain. There's a whole bunch of books there. You can just download them, do whatever you want. Other things including outgoing links on Reddit, the text that appears there. So there's a lot of sources of public data on the internet, and typically all this data is fed into these machine learning models, which are the biggest and most popular ones nowadays. And it turns out that if you start with that sort of public data as a good sort of prior for whatever you're going to do next, it can give you a lot better utility if you do differential privacy on top of that on whatever sensitive data sets you care about. Like, the analogy I want to draw is, imagine you want to, in the end, do some sort of medical prediction in the sense that you have some symptoms and you want to predict what sort of illness someone has. It's much, much easier to do that if you know English beforehand, before you try to just go straight to predicting people's diagnoses. So maybe the way of thinking about this is downloading all of the internet and trying to extract out the things which are not sensitive, like what it means to know English, is a good thing to do before you try to do anything that's privacy sensitive on top of that. And so I've been looking a lot into how much can we push public data for private ML and what are the pitfalls. Cool, but that's basically where I want to wrap this up, and I'm happy to chat about questions, differential privacy, machine learning, whatever. I hope I got across that privacy concerns in machine learning are very real and very common if you don't take it into account. Differential privacy can help alleviate many of these issues. There's a lot of challenges I didn't talk about, but you can see at least in some cases it gives you a rigorous way to at least fight back against these privacy violations. But there's still a lot of work to do. Cool, thank you.
Does anyone have any live questions?
Yeah, so just looking at that, like some examples, we had 20 smokers, and so like what the data set was trying to tell us, like, oh, 20% of the population smokes.
Yes.
But then we look at that second Laplace, like the noise, and like how would we get any information from that? Like if we were shown that, I don't know if 2% smokes or like 40 or whatever. Like, at what point do you just change the data set and it becomes kind of obscure and useless?
That's a really good question. I think there's often a challenge when you're doing differential privacy to figure out where's the trade-off between utility and privacy. For example, if you want 0 dp, which is like perfect privacy, you just make up a number. It's something totally unrelated to your data, which is of course totally useless. And then if you put infinity, then you'll add no noise and it'll just output the number exactly. So the question is, there's sort of two things you have to do. One is you have to figure out where exactly is the trade-off. Maybe, you know, the chance of coming up with this 2.4 is just too bad. It would ruin our estimate. And so you're going to say, okay, that's too much noise for the utility we're going for, and figure it out from there. Another thing is whenever you're doing analysis on data which has been privatized in this way, you can't just use it in the same way as before. You probably have to do some sort of analysis to make sure that, you know, you take into account, okay, I think it's like 11.45%, but I know this is the noise, so what does that actually mean about the true number? So yeah, you definitely have to be careful and take it into account whenever you do privatization. Yep?
So privacy helps in areas where you sort of use sensitive data to train your model. But then what about explainability? When you deploy model trained with sensitive information in sensitive areas, like who gets this organ transplant, or like some sort of financial decisions? How would you, like, adding noise at every step, as you mentioned, is a trade-off between privacy and utility. But after a certain point, how would you try to explain these like off results in a way that is convincing enough? Because even humans initially would try to argue with just the output. But then at some point you would go back to what you learned at using case studies, or sort of like refer back to what has happened in the past. So how do you see like the balance between privacy and explainability?
Right, good question about privacy versus explainability. So yeah, let's say that, like, another thing I'll mention is that there's broadly a big field of machine learning known as like trustworthy, or like trustworthy machine learning, which includes things like privacy and robustness, but also includes things like fairness and explainability and stuff like this. And often, many of these desiderata are at odds with each other. So if you need more privacy, you get less explainability. To answer, I feel like in this specific case, maybe I'll say something similar to what I answered the previous question, in the sense that when you're doing an analysis on downstream data, you have to really take into account where that data comes from. Like, that's what trained statisticians often do. Like, you know, there's some estimate we have, okay, even in a non-private setting, we can say, we got this estimate that maybe 20% of the population is smokers. But maybe this is a biased subsample of the population. Maybe you were at a specific place where a lot of people are smokers, and so you had some sampling bias. So you have to account for that in your error as well. There's another form of error that you're going to have to account for, and kind of a similar sort of calculation when making inferences from privatized data.
It's almost like treating the privatization noise as another source of error.
Exactly, yeah. Many analyses treat it as another uncertainty in the overall thing. But I think one thing, a lot of people sometimes complain about differential privacy, about, oh, you take these perfect data and then you add noise to it and ruin it. But then these people often neglect the fact that the data that we often collect is already noised, like in the sense that there's always imperfections. For example, like there was a nice study done by some of my friends at Carnegie Mellon, where a lot of people have been complaining that this totally ruins the census, which is used for a lot of districting and allocation of things. And so if you look at how much misallocation of resources like money, then there's like billions of dollars of misallocation due to the privacy noise. But if you take into account all the other sorts of noise that go into the process, it's actually like orders of magnitude bigger. So it hurts your data, but there's also other sources of error that you have to take into account at the same time. Yeah, you have another follow-up?
Yeah, how do you determine how much noise to add?
Yeah, how do you determine how much noise to add? I guess, like, I can say that if you start with kind of a privacy guarantee, like how private do you want it to be, which is often a difficult thing to determine, like in the sense that I want this definition of differential privacy with some value of epsilon and delta. Now how you come up with that is a difficult question, and you kind of have to, you have to put a lot of thought into that and when you try to determine what's reasonable. But say you have that, then that tells you how much noise you can add. The more private you want it, the more noise you have to add, naturally. Cool. You have a question over here?
Yeah, before I ask the question, just a comment. Like when we say that when there's no differential privacy and the output just a tiny change in the input changes the output, could we say that we're overfitting our model? Because even like technically, if there's a small change in the input, we shouldn't really change the output anyways, right? So are we just like stopping the overfitting with differential privacy?
Exactly. That's a nice observation. The fact that ideally, a small change in your input shouldn't change your output much, in the sense that, for example, if you have a machine learning model, adding one data point to it shouldn't dramatically change it, because like, say you have a classifier on what pictures of cats are, you add one more cat, then it probably shouldn't change things that much. So, yeah, like somehow that observation is why at least this notion of privacy is compatible with learning. And yeah, there's actually strong connection between saying, for example, if some model is differentially private, then it is guaranteed to generalize. So yeah, there's definitely connections here. I don't know if did I answer your question?
Yeah, that's great.
Cool. Is there another question at the back?
Yeah, so it seems like differential privacy and this idea has been around for like a little while, but like even just in recent years, like we had the Netflix issue, like those kind of issues are still happening like a lot. So is differential privacy working, or is companies not implementing it, or like why is there that discrepancy?
Good, yeah. So the Netflix example in particular is from 2008. So it's like around the time of this whole thing, of this being introduced. I think people in many organizations are getting more savvy to what's going on, but I think it's just everyone wants a free lunch, in the sense that thinking, oh, when you use differential privacy, I won't lie, you do get a hidden utility. Like your things will be less accurate, they'll be less useful. So people want, okay, why don't we just try something else, like maybe anonymize the data or use some other privacy preserving method, and hope that works better. But I think time and time again it's been shown that these things don't necessarily work. So I think hopefully people are learning over time, but it's also just wanting everything for free. Do you have another question over here?
Oh yeah, actually. So just unrelated to differential privacy, how much privacy do you think that like the average citizen should have? Like, do you think like it's okay for Facebook to collect our data and to use it to, give us advertisements? Like, because it seems to me like most people don't even care about their data. Like they just give out their data for free, right? So there's no like money to make in privacy because people just give out their data. Nobody's willing to pay for privacy, right? Like, do you agree with that? What are your thoughts?
Yeah, that's super true in the sense that like we talk a lot about privacy, but everyone when they see a website where they want to access something, they'll click allow all before even, it's like almost a reflex at this point, to be honest. So it seems like there's sort of a disconnect here, how we feel like we should value privacy and how people seem to in practice value privacy. I think there's some things which are literally like there are some, I think, hard regulations and laws which prevent various uses of data, like for example GDPR is big in Europe. Canada is in the process of introducing its own federal privacy legislation, and so for things like this they still do give some barrier of protection. I hope that over time people will become more cognizant of privacy and more legislation will help people act more in line with what they actually value. Because, yeah, for example, I think the Cambridge Analytica Facebook thing from like, I don't know, 5-10 years back, I don't remember how long now, That kind of showed that people giving up a little bit of information can have massive impacts on, say, democracy and the outcome of elections. So hopefully, as these things happen, people will realize a bit more that, oh, actually, even my little bits of data can add up overall. So I hope things get better, and I think with privacy legislation being rolled out, it will. Cool. Was there another question over at the back there?
Yeah. So we talked about like how there's a hidden utility, and that's like I think our list was that too. But is it possible to formalize like a hidden utility just as the privacy bounds that we created?
Good. Is there a way to formalize the privacy utility trade-off in some sense? In some simple settings, for sure. Like I can tell you for mean estimation of a Gaussian distribution, then if you want this level of privacy and this level of accuracy and it's this dimensional, we can up to constant factors tell you what you can do, which is, you know, okay for those settings. For some of these machine learning models, even without privacy, we have no idea really why they achieve such accuracy. So I don't think we don't really have a way of quantifying how big the hit will be, except you run it and see how big a hit you get, and then go from there. Yep.
Does differential privacy solve the problems of privacy in that way that you mentioned before? Like, does it make it impossible for people to determine who is part of the training data, or does it just make it harder to find out?
Good. So actually, you said Cambridge Analytica, right? Were you referring to the Cambridge Analytica case? Like, would it protect against that?
Sure, yeah.
Sure. At least in that specific case, I actually think differential privacy wouldn't necessarily protect against that thing, just because it's not meant to. Because my impression, I haven't looked into it too much, but I thought it was basically they looked at not only individual data, but aggregate individual data, which is something that differential privacy actually enables, because that's kind of the design. You want to infer things about aggregates over a population rather than about individuals. So it's not a panacea. It's not going to solve all the privacy-related problems, but it can in certain settings.
So it adds a layer of difficulty in discerning the source.
I'd say, yeah, it definitely protects against types of things where an attacker looks at the output and figures out things about one person.
Would knowing how much noise was added to this help, like, someone figure out the source faster?
Good, yeah. So like knowing the privacy parameters, how much noise. So generally in security and privacy, what you assume is that the adversary is very, very knowledgeable. They know pretty much everything. They know exactly what algorithm you're going to run with exactly what parameters. They just don't know the actual the value of the noise that came out. Like when you sample the Laplace noise, whether it was 1.3 or whatever, that's the only thing they don't know. So the assumption is very strong, or very weak, that they know everything, including how much noise is being added. Cool. Any other live questions? I feel like you have something on your mind.
Sure. Let's talk about like privacy. How much, like if we're looking at, like I look at hospitals and like I was told that hospitals like regularly get hacked, and that if you work at a hospital, it's basically guaranteed that all your information gets taken. So like if you're looking to solve big privacy problems, how much of it will be like technical solutions like differential privacy? How much of it will be legislation solutions like, you know, regulations? How much of it will be non-technical problems? Like, can you give like the landscape of like what the different approaches to improving privacy are, and how well each different approach is working?
Yeah, it's tough. I think it's tough to give like a full taxonomy of all these things, but yeah, they all kind of go hand in hand in the sense that suppose there's no privacy legislation at all, companies can do literally whatever they want with your data, then they probably would, right? Why not? If you can make more money, then go for it. So legislation and, say, technical solutions probably go hand in hand in the sense that legislation inspires technical solutions as well as non-technical solutions. I think, you know, one critique, which is also related to the previous thing you said before, is maybe some people might wonder why do we even bother with this sort of privacy stuff? Maybe people just give it away. Maybe there's other vulnerabilities, but it's kind of like you don't want your responsibility to be the one or sorry, your position in the whole pipeline to be the one which is like leaking the information. Even if others are, it still seems like something worth doing to protect.
Thanks.
Yeah. Cool. Anything else? Yeah.
Just curious, like, other than just adding noise to the like data set, are there any other layer approach to this kind of problem? Because it's somehow like, if we're just adding noise, it's like a pre-processed data set. So like, it's sort of simple, right?
Yeah, there's definitely a whole lot more that is done, and and analyzing it as well. Like one way is like kind of random sampling procedures, in the sense that like maybe you're trying to choose from a set of different outcomes, which may be of different qualities, and if you sample from the right distribution, depending on how good they are, then that will be appropriately private just by itself, and that's not a noise addition mechanism. So yeah, there are stuff outside of this, and there's also many different ways to add noise in specific ways, and there's things that even interact with noise. For example, like imagine when we're doing the summing together of bits, maybe I only actually subsample and I pick only one in every 10 people. That actually gives a stronger privacy guarantee when I add noise afterwards. So like, there's more to it, yeah. Yeah, back there.
So I was trying to apply documentary privacy to just anonymization. And I was wondering.
Trying to apply to what? Sorry, say again.
To anonymization of data.
Okay.
So you did mention a bunch of pitfalls with just anonymization, because general trends still remain, and you can still figure out who was part of training data. But what if you try adding noise just to what can be personally identified to a person, and try to anonymize by adding noise to those things rather than all of the data that you want to inference?
Right, great question, yeah. So like, I wasn't really clear what I meant by anonymization. Like, this type of anonymization does not work, where you just take the data set, it has some names, throw out the names. That is not private, because you can still figure out a lot of stuff based on the other features that they might have. What you can do is, like you said, add noise to, say, some of their features in the data set. This actually, it turns out, like, rather than the final statistic, and this actually turns out to satisfy a form of differential privacy known as local differential privacy, where you kind of noise individual data points in some way, rather than the final statistic. Now, there's pros and cons. The pros are that this is a stronger privacy guarantee, like nobody else ever sees my data. The pro number two is the fact that you can do whatever you want afterwards with this data after you noise it. The con is that you need much more data to get the same accuracy downstream. Yeah, like noising each individual's data and then averaging them versus averaging their sum, noising their sum rather, then the latter approach needs much less noise.
So does that mean that localized differential privacy takes a greater data capability?
Totally, yeah. It's almost unusable unless you're doing the most basic of statistics at like Google scale. So it's pretty tough to do anything, and people have been coming up with more intermediate models where it kind of gives you local style guarantees, but with less noise. There's something called the shuffle model if you want to look up something later. But yeah.
Do you want to take a few online ones?
Yeah, for sure.
Okay, I'll just read it out. Where do you see the future of techniques to make machine learning models privacy preserving? How do techniques like differentially private federated learning need to be extended?
Yeah, but beyond, so like the way I've kind of given this talk is, focus on differential privacy, but there's a lot of other things which fit into the space. For example, federated learning is a popular term as well, multi-party computation, and then things beyond this. It's really tough to say because all of these things work together at different levels. At least for differential privacy in particular, I feel like one of the exciting things is understanding, how to use public data that I kind of mentioned. Another thing I will say is that I think hand in hand with that, I think one problem that we've got which is actually coming to a reckoning right now, is what is publicly available is not necessarily public data, and that's not even like a technical question or anything. It's just like GPT-2, 3, these are trained on like just info downloaded from the internet. And like I said, much of it is copyrighted personal information. And that's like a disconnect because we might think of that being publicly available, but it's also things that are not okay to train a machine learning model on. So this is not even a technical question. I think coming to grips with that is going to be a big problem. It in fact already is, because there's lawsuits over some of this generative AI which can generate images. For example, if a machine learning model generates an image which looks a lot like someone's style, is that a copyright violation? So I think grappling with this, especially in a legal context, is something that's coming up very, very fast.
There's just one more online. It's a bit of a paragraph. Implications for sharing data for ML training. For example, governments or social media companies sharing large data sets for model training without risk of data leaks. Also, if I recall correctly, Netflix tried the above and botched it up, which resulted in user data leaks. So why would people release data sets using differential privacy if potential for data leak is high? Also, what about future data leaks using techniques that aren't discovered yet?
Yeah, great. So the last part is a good question. What about future attacks that people haven't discovered? The convenient thing is differential privacy is a very strong guarantee that says essentially anything ever that happens in the future will still, no matter what happens, we will still enjoy this differential privacy type guarantee. So it's protect against future releases of that sort. So that's very nice and convenient. And I guess the first half of the thing, I guess I'd give the same answer in the sense that as long as things are properly released with differential privacy, then you have a rigorous guarantee. A problem with the Netflix thing is that they just hoped for the best. It was a heuristic guarantee that they gave. But a rigorous guarantee will guarantee that in the specific threat model, like the things you're worried about, then nothing bad can really happen in the future.
Any more live questions?
Yeah.
Can differential privacy be used for any sort of ML application, or is this localized to NLP? Can this be transferred over to computer vision?
It's very flexible. In particular, that algorithm I mentioned, DPSGD. Essentially, anything that is trained with stochastic gradient descent or gradient descent in general, which is almost every neural network model for one thing, it can be privatized in a very straightforward way, like just literally change a few lines of code, and then it's okay. So yeah, it's very versatile, surprisingly versatile for how simple the algorithm is. Yeah, there may be some cases which are a little bit trickier to privatize, and you have to do different things. For example, if you want to do a nearest neighbor classifier or something. But at least for neural networks or anything that uses gradient-based optimization, this is a drop-in replacement. Cool.
Well, if that's it, we still have refreshments up there. You can hang around for the next few minutes. But again, we want to thank you so much for giving us your time today. So if we could just give them another round of applause.
Yeah, thank you again. Like I said, the pleasure is mine. I think it's a lot of fun always engaging with undergrad. I think people had a lot of excellent questions. I'll just drop, if you want to learn more about differential privacy, there's a few resources I can point towards. One is differentialprivacy.org, which has a bunch of posts and a bunch of resources. If you click on the resources, you'll find a course I taught here back in fall of 2020. All the videos are online, so you can self-study. Also, follow me on Twitter, @TheGautamKamitz. Yeah, I'm happy to answer any questions here or later.